Welcome, this is question 6 for Edexcel C4 June 2008 past paper. Now, this is a vectors question, okay? We're given these two lines, obviously line 1 and line 2. They're very creative, Edexcel, with their names. I mean, I would have called it Jimmy Bob Cricket and Jeff, but, you know, that's probably why I'm not head of Edexcel. Anyway, and apart from the fact that I yet have the qualifications. But anyway, so this line 1, they put R as just a position vector, is equal to minus 9, 0, 10, which is just a point on the line, remember, plus lambda 2, 1, minus 1, which is the direction vector, okay? Line 2, similarly, R is equal to 3, 1, 17, and you add mu brackets 3 minus 1, 5. Now, obviously, I've converted that from the line equations that you get given in the actual paper. Now, there's one thing that I want to point out straight away. You have to look at the I, J, and K and be able to understand in terms of, because I is the unit-based vector for X, J is the unit-based vector for Y, and sorry, I do apologise. K is the unit-based vector for Z, which is what comes out on the page. I really do apologise. I've got a pretty sore throat, as you can tell. So this video, it's not going to be a maths tutorial, it's just going to be me slowly dying. So I'm assuming that'll be a benefit for many of you. Anyway, so really, as I said, it's being able to understand what I, J and K is, because when you first look at the line equation for L1, it says minus 9i plus 10k. Okay, it doesn't say minus 9i plus 0j plus 10k. No, it just says minus 9i plus 10k. And you might think, oh, well, k is the next one along. Surely there's only two parts to this direction vector. Well, you're mistaken there, obviously. Okay, and that kind of goes off from, you know, it's just being able to understand what I, J and K represents. Okay, right. So show that line 1 and line 2 meet and find the position vector at their point of intersection. Okay, now what we do is we make L1 equal to L2. Okay, so you could do, okay, so minus 9, you could just simply write the equations as you would do if this was a y equals mx plus c line. But obviously we're going to need to do a bit more detail than that, because, you know, this is C4, not C1. But, you know, C1's for the thick people, obviously. That's why I'm redoing it. Okay, okay, so I'm just simply writing out the equations of the lines again. You don't have to, but it, you know, helps me to explain it. So, you know, stuff you and everything. Okay, so how do we prove that they intersect? Well, basically, this lambda has to have a constant for each of these. This lambda is the same for each of the I, J and K. But because we've got a mu here, and obviously we've got different values, the value of mu and lambda is going to be different. It might be different, it does end up being different, but that doesn't matter. Basically, for a constant value of mu, it will give us a position on the line L1. And for another or different value of mu, that will give us a value of a position vector on the line L2. And they have to be the same, okay? So for one value of lambda and one value of mu, they must have the same position vector or answer, okay? So basically, the I, J and K on this side will equal the I, J and K on this side. So we come up with 4 equations, okay? Now, obviously, the key difference is to realise that's lambda and that's mu. Not do what I did on my first attempt and just put them both as lambda because I didn't read the question properly and end up getting lambda to be several different values, which is obviously wrong, as you can tell. Anyway, as I said, come up with 4 equations. So the first equation I'm going to derive is just by comparing the I values on this side to the I values on that side and making them equal, obviously. So minus 9i plus lambda times 2, or plus 2 lambda, is equal to the i's components on this side, which is 3 plus mu times 3, or 3 plus 3 mu. Okay, so that's the first equation. Equation 2, compare the j, so it's 0 plus lambda times 1, or 0 plus lambda. I include the 0, you don't have to. Okay, and then that's equal to the i's on this side, which is 1 plus mu times minus 1, or 1 take mu. Okay, equation 3. Compare the k's obviously, so it's 10 plus lambda times minus 1, or 10 take lambda, is equal to 17 plus mu times 5, or 17 plus 5 mu. Okay, so what we do is we can rearrange one of these. Well, obviously 2 is lambda equals 1 take mu, so that's quite a nice one actually to put into something. We're going to sub it into one of the equations. Obviously we can't sub it into itself, that's logical. Now the easier one that I would sub it into is 3, because obviously you're going to see it's nice and simple, whereas this looks a little bit more difficult. Not difficult, but just a little bit more. Okay, so what we're going to do is sub equation 2 into equation 3. And what we're trying to do here is find the value of mu and lambda, so we can find the position vector where they intersect. Okay? Right, okay, so we're just going to sub this lambda into here. Okay, so it's 10 take lambda, and I'm just going to write in brackets, because obviously we're going to have a double negative here, as you can see. And some people do make the mistake of, even though it's a double negative, they'll still assume it's negative. Okay, and that's equal to 17 plus 5 mu. Sorry about my 5. Okay, so then it's just a case of expanding this, so 10 take 1 plus mu is equal to 17 plus 5 mu, or in other words, 9 plus mu is equal to 17 plus 5 mu. Okay, so you rearrange that to get mu. You get mu is equal, so minus 8 is equal to 4 mu. So therefore, mu must have a value of minus 2. Okay, so you could work out the position vector on the line L2 with the value of mu as being minus 2. Okay, now you can do that now or wait till you do that afterwards. Personally, I would do it now. Okay, so if we sub in mu to be minus 2 in the line L1, now obviously you've got a new line of working for this. Okay, so what you do is just work it out. So 3 plus minus 2 times minus 2 times 3. Okay, that obviously gets you minus 3. Okay, and then 1 plus minus 2 times minus 1 is obviously 1 plus 2, which is obviously 3. And then 17 plus 2 times minus 2 times 5, sorry, that is 17 take 10, so that's obviously 7. Okay, so it's minus 3, 3, 7. And if this position here lies on the line L2 as well, therefore we can say they intersect. Now there's 2 ways you can go around this from now. You can either work backwards, so put this as the position vector for L1 and see if we get a constant value of lambda, or you can do what we did before, sub in a value and work out what lambda is, okay, and then work out the position vector and work out if they're the same. Well, to make things simpler, I'm going to do the same method that we did to find the position vector on L2, but obviously we're going to need to find lambda. Okay, so we know lambda is equal to 1 take mu. So I'm going to come up with a new equation. I'm going to label 4. So equation 4 is just the rearrangement of equation 2 to make mu the subject. So obviously you add mu and take lambda, so mu is equal to 1 take lambda. Okay, and then we're going to sub that into equation 3 again. We can completely ignore equation 1. Okay, so follow the same kind of principle. So 10 take lambda, remember I'm not subbing in for lambda, I'm subbing in for mu, is equal to 17 plus 5 mu, or 17 plus 5 times 1 take lambda. Okay, and then the case is simply expanding this and simplifying it down as we did before. So 10 take lambda is equal to 17 plus 5, sorry it's not, take 5 lambda. Okay, then it's just a case of, as I said, simplifying down and rearranging. Okay, so you will get lambda to be a value of 3. Okay, if you were to do that. Now I don't need to go into how that is, hopefully you can just work that out yourself. And then what we're going to do is sub this value of lambda into equation for the line L1, and if you were to do that you would get a value of minus 3, 3, 7. Okay, Now, what I would do at this point, okay, so that's the point of intersection, minus 3, 3, 7, or minus 3i plus 3j plus 7k. Okay, so that's the point of intersection. And sorry, that's the other part of this equation, what it's asking, what it's asking, sorry. So what I would now do is we're going to move on to question B. Well, you would do that, yeah. So hopefully not just give up, okay? So that was part A. Quite a bit of a challenging part, but nothing that you can't handle. Okay, now we need to show that L1 and L2 are perpendicular to each other. Now the only way we do that is by showing that the first thing you would write in this is if they are perpendicular, then the dot product of the two vectors will be 0. If they are perpendicular, the dot product of the two vectors, or in this case, because we've got equations of lines, the dot product of the two direction vectors, which is this 2, 1, minus 1, and this 3, minus 1, minus 5, when you do the dot product of them two, they should come to 0. Okay? So hopefully you wrote that sentence somewhere on your answers. Okay, so what we're doing is the dot product of 2, 1, minus 1, which is the direction vector of L1. So 2, 1, minus 1, and we're timesing that by doing the dot product of that with the direction vector of L2, which is 3, minus 1, 5. So that should come to 0. Okay, so if we do 2 times 3, add that to 1 times minus 1, and add that to minus 1 times 5, that is equal to 6 take 1 plus 5, which obviously is 0. Okay, so therefore, as it is 0, they are perpendicular to each other. Now we know they're perpendicular, and this is the point of intersection. What I always like to do is draw a little sketch, even though it doesn't necessarily ask you to. It is very helpful, okay? So, now it doesn't really matter which way round you're drawing in terms of L1 and L2, okay? But, you know, the principle of drawing it it's not asking you to, so obviously it doesn't matter if you don't draw it perfectly. Okay? So, I'm going to draw something like this. So now we know the perpendicular, we can draw them like this. Okay, so they're perpendicular to each other, so all these little corners here are going to be 90 degrees because they're perfectly perpendicular, so it all works out. Okay? Right, okay, so part C. Well, it's not asked us to do anything with this yet, but he's going to. Okay, so just corner this off here, part C. Part C is asking us to show that point A with the position vectors, so the position vector 5, 7, 5, 7, 3, show that lies on the line L1. Okay, so it's the kind of thing you might have done in part A, sorry. Okay, so we've got to show that lies on L1. So just make that equal to the line at L1. So minus 9, 0, 10. Okay? And then you plus lambda times 2, 1, minus 1. And if it lies on the line, it should give a constant value of mu, of lambda, sorry, for each I, J and K part. Okay? So what we're going to do is create a couple of equations here. So equation 1 is equal, comparing I, so it's 5 is equal to minus 9 plus 2 lambda. Okay. Equation 2, 7 is equal to 0 plus lambda. So obviously lambda is 7, you can see straight away, but we're going to carry on comparing them all. Okay. And 3 is equal to 10, take lambda. And if you were to work all of that out, obviously you would get a constant value for lambda is equal to 7. So therefore, point A lies on the line. Now, I'm not going to, as I said, I'm not writing all that down because, as I said, hopefully I'm not gone too fast for you. Okay, right, now this part D is now critical to draw this graph. Okay, so weirdly enough, I can just write point D. It looks like I've anticipated the future. Imagine that, anticipating what I'm going to talk about in my own videos. Crazy stuff. Anyway, almost as crazy as my hair, even my head as well. Okay, so anyway, the next little bit of information we're told, point B is the image of A after the reflection in the line L2. What the hell does that mean? Okay, so let me try and translate that for you. And let me make sure I'm translating it correctly. Okay, so basically these lines intersect at this point here. And we're going to label this point here. Okay, and we say that was minus 3, 3, 7. Okay, so let's break that down, that bit of information we've just been told. Point B is the image of point A in the reflection line L2. Okay, this is the reflection line L2. Okay, so it's the is the image of A after the reflection. Okay, so what does that mean? Well, it means obviously if you would draw, we know point A, which is this, lines on the line L1. That's what we've just proved. So we draw it somewhere on the line L1. Now it just happens to be over here. Okay, past the past this. Okay, and what I'm going to draw is on that is point A and draw its coordinates, which is 5i plus 7j 3k, or 5, 7, 3. Now, as we know, this point B is the reflection in the line L2. What that essentially means, as far as we're concerned, is that the distance from the intersection to A is going to be the same as the distance from the intersection to B. Now, it's obviously not going to be further along L1 because it's been reflected in L2, and we assume that's the only time it intersects. Okay, so obviously B is going to be somewhere over here. I'm just going to give it I, J and K coordinates. I don't know, you could come up with anything if you wanted. Okay, trying to think of something. I can't come up with I, J and K because that'd be stupid, that'd confuse you. I'll just call it D, E and F, okay, which just points for B, okay? Right, that's just D, E, F is just a position vector for B. Okay, now we know the distance between this intersection and A is equal to the distance from the intersection to B. So the difference in the I, J and K coordinates is going to be the same. So the difference between the A's I coordinate is going to, the distance between the change in the I coordinates between A and the intersection is going to be the same as the change in the I coordinates from the intersection to B. Okay, so let's work out the change in the I coordinates and the J and K coordinates from the origin to A. Not the origin, so the intersection. Okay, so the change in the change in the I coordinates is 5 minus 3, so the change is 8. Okay, the change in the J coordinates, so you just put a little thing there, is 7 minus 3. Okay, so that's changing 4. The change in the K coordinates, because obviously B is going to have a K as well, is 3 minus 7, so that's minus 4. Okay, so basically the change in the K coordinates is 4. Alright, now you can work out if you wanted to that the I coordinates have been reduced by 8, the J coordinates have been reduced by 4, and the K coordinates have been increased by 4. Okay, so what we're going to do is apply that method to B. Okay, now that's the distance between the intersection and A. As I said, the change in the coordinates is going to be the same from A to the intersection than the intersection to B. Okay, so kind of applying this logic, but now we need to sort of take them away essentially to get to B, because remember we're moving along this line, which means obviously certain things. Okay, so if you want to, you can compare the coordinates. Okay, just looking what I did. Okay, so let's call this. This is how we're gonna work it out. All right. So we're currently at minus 3. So I'm gonna write all the coordinates in for the intersection. Okay, because we're gonna be changing from that. So first thing I'm gonna write in the I, J, and K coordinates of B. Now it's not necessarily the end coordinates because we're going to be altering these by the same amount that we did to get to A. Okay, but just doing the opposite of it. Okay, well, because we took 8 away to get from A to the intersection, and we're going along the same path, we're just going to take another 8 away. Okay, so it's minus 3, take 8. And as we took 4 away from the J coordinates to get to intersection, because we're going the same way again, we're going to take away 4 from the j coordinates of the intersection to get to the j coordinates of B. So we take away 4. Okay, but when we went from the point A to the intersection, we increased our k coordinates by 4. Okay, so we're going to do that again because, as I said, we're going the same distance. So it's 7 plus 4, and if you work out them sums, you should get your position vector of B, which you should get to be minus 11, minus 1, 11. Okay, and that's your position vector of B. Okay, so hopefully that's explained it. I do apologise if it's not been the smoothest video, but as I said, vectors is quite a difficult topic. Okay, so anyway, thanks for watching. Hopefully, as I said, it's explained something. I do find vectors the trickiest topic in C4, and also the trickiest topic in M1 because they are quite similar. Okay, so thanks for watching. Hopefully, as I said, it's been not a complete waste of your life, although I'm starting to wonder what the hell am I doing with mine, and I'm sure you'll be asking the same question in the YouTube comments. So anyway, thanks for watching, and we'll see you soon, hopefully, in a non-weird way. So, oh God, had to screw up a video, eh?